In this tutorial, we're going to talk about how to calculate the electric field of a radiating dipole. Where we left off last time was that we knew what the magnetic radiated field of a dipole was. And this is the expression over here. And to remind you what the geometry of this is, we have an oscillating dipole at the origin. We define that dipole moment by thinking about a constant vector p naught that in this picture points up. This dipole is oscillating in time, that's the e to the minus I omega t dependence there, and at some location in space, many wavelengths away, so what we call the radiation zone, we have a point where we located by vector r, and we'd like to know what the magnetic and eventually electric field is there. How are we going to find the electric field? We're going to start with Maxwell's fourth equation for the curl of the magnetic field, which is given as written over here, and that's where we'll begin. Now we're out in space over here, so we're looking for in the radiation zone. The only charge in our world is this oscillating dipole, so there's no current density out here. So out at this location, we can simply delete this term. There is no charge out here. So that immediately gives us mu naught times epsilon naught, which I can write as 1 over the speed of light in vacuum squared, times dE dt. So already we've gotten things a little bit simpler. And then we note that the electric field oscillates in time just according to e to the minus I omega t, like everything else in this problem. If you shake a dipole sinusoidally in time, the magnetic and electric fields will at any point in space oscillate sinusoidally in time. They may point in different directions. Certainly the B and E field are not going to point in the same direction, and they may vary with position. They may not be the same everywhere spatially, but temporally their time variation is just e to the minus I omega t. So that means that the electric field as a function of position and time is equal to some spatial dependence times e to the minus I omega t. So the time derivative of the electric field just brings down a minus I omega and otherwise leaves everything else here the same. So the derivative of E with respect to time is actually E itself multiplied by minus I omega, a property of exponentials. That makes life very simple here, because now I can write that this is equal to 1 over c naught squared times the minus I omega factor from taking the derivative of this, and then everything else combines back together again and just gives me E. So now I have that the curl of B is equal to some constants times E, and I can solve this, and I can therefore isolate E by itself and say that the electric field in this radiation zone is just equal c naught squared over omega times the curl of the radiated magnetic field. So now I've almost got an equation for E for the electric field of the dipole. I just have to take the curl of this big expression, and we're going to use the same trick that we used, or the fact that we used in deriving the radiated magnetic field to take the curl of the radiated magnetic field. We just look at this part of B rad. This is the only place where B rad depends upon space, and it's the same as in the derivation of the magnetic field. It's e to the I k r over r. Nothing else here, and the rest of it constitutes a vector, which we'll call G. That's the rest of this expression, and the part inside the box we're going to call scalar F. So the magnetic field equals scalar F times vector G, the curl of F times G, and we remember what this formula is for the curl of F times G. The curl scalar F times vector G. I'll just make this appear. Now it's a little bit subtle You might be saying P cross R hat. Well, that looks like it has some R dependence. So how do I know that it's the derivatives, the curl of G, go to 0? And they don't go exactly to 0. But in the radiation zone, I'm just going to assert that far from the origin, this term becomes negligible. So I'm going to write that going to 0. We might deal with that elsewhere, not here. Curl of G goes to 0 far away from the origin. So we're left again with G crossed into grad F. And I'll remind you also that the grad of e to the I kr over r, we derived that last time as well. This is what it's equal to, as it was before. And since we're in the radiation zone, where we're far away from the origin, many wavelengths away, 1 over r is much smaller than k. So now we're ready to plug into the curl of B rad. Let me write out some terms. We'll start with the I c naught squared over omega. Then I want to write minus G vector. So minus and another minus gives me an overall plus sign. I have mu naught omega squared over 4 pi c naught. I have e to the I kr over r, and I still have the e to the minus I omega t. So all of that stuff is still here. E to the I kr minus omega t over r. And then I've got a factor of ik. And then I've got the vectors. So it's G cross grad F. So G has this as its vector. Dipole magnitude vector crossed into r hat. And that vector gets crossed again with r hat. So there is our entire expression for the radiated electric field in the radiation zone. Now I'll just do a little bit of cleanup. First, look at my factors of omega. I've got omega in the denominator, 2 omegas in the numerator, and I've got a k here. Remember that k equals omega divided by c naught. So this k's omega kills that omega, so I'll end up still having a factor of omega squared. The k has a c naught in the denominator. Here's another c naught in the denominator. Here's two c naughts in the numerator, so no c naught survives at all. I've got 2 factors of I, nothing canceling that out, so I've got a minus sign. And I've got something that's going to end up looking a lot like the B expression here. I still have a factor of omega squared. I have a 4 pi in the denominator, but not a c naught. Then I again have my spherical wave with harmonic time dependence, e to the I kr minus omega t over r. And I have a slightly different vector direction. P naught cross r hat crossed again into r hat. Now just think about what we've got here a little bit. Look how similar B rad and E rad are to each other. They have exactly the same sort of dependence on R and on time. The orientation of the E vector is a cross product of the B vector's direction, which is into and out of the page, and the R vector, R hat vector, which is in the plane of the page. So what's orthogonal to this direction and into and out of the plane of the page? That would be this direction. So this oscillation here is going to be the direction of E, orthogonal to the location vector R and orthogonal to B. So we get this result that E is perpendicular to B, which is perpendicular to r. These three vectors in the radiation zone are orthogonal to each other. We still have that p naught cross r hat has a magnitude of sine theta, which tells us something about which directions fields radiate most strongly into. Does this cross product bring on any sine factors? No, it doesn't, because this is the direction of the magnetic field, and the magnetic field's into and out of the page. That's orthogonal to the r hat vector. So these two vectors, this one and this one, make a 90-degree angle with each other. So this just brings in a factor of 1. So there's no extra factor there. So the last thing to notice is that the electric and magnetic fields have almost the same magnitude. This has a magnitude of sine theta. So does this. Everything else in the expression is exactly the same, except that E doesn't have a C naught in the denominator here. So that means that the magnitude of E rad at any location is equal to C naught times the magnitude of B rad.